Hello, my name is Brittany Alvarez, and I did my project and essay on change detection imaging. So what is change detection imaging? It is an information extraction process which utilizes the decision-making capabilities of a computer to recognize and classify pixels on the basis of their digital coding. This is straight from the textbook on chapter 9, page 2. Sorry, that was my cat. It's straight from the textbook from the Sabins and Ellis, chapter 9, page 244, if anyone is interested. Change detection images provide information from satellite image changes in surface detection over time using 2 or more images. So most of the articles that I came across, they only used 2 separate images, one being before an event and one being after. But you can use more than 2 to do any kind of project. So each image has a set of pixels that contain DN values, which are digital numbers that are subtracted to determine a change or the lack of a change. In detail, each pixel in the image is assigned a number that represents a color depending on the band that's used. After 2 images are obtained, the pixels are subtracted from each other, resulting in either a positive, negative, or no change in those DN values. This creates this creates a new image with the resulting pixel DN values. Typically, the negative values are associated with dark colors, positive are associated with lighter colors, and 0, aka no change, is associated with like more gray or neutral colors. And this is all depending on the band that is used. It can be varying colors, but with the same idea. So this is just an example of a pixel grid with some DN values. In a real world application, the original photo contains, or the one on the left, contains the value of 3 in the middle, and the second image on the right contains a value of 5. This will show as a difference in the 2 images visually, so when we look at it, we can see a visual change. And because of these DN values, the computer will detect the differences to process further information. So these images are textbook examples of change detection images. The first one, image A, is a photo taken in 1986 excuse me, by Landsat using band 3. Image B is the same area taken in 2010. Image C is using the grayscale that I mentioned earlier to show the same simple pixel subtraction method. So this would be if, excuse me, since 3 and 5 from this slide, you would subtract 3 minus 5. So you would actually get a negative value, which would be -2. So that image would be dark. And in the third image, if you guys can see in the center on image A, it's kind of more white or like a lighter gray. In image B, it's a little bit darker in the center. So you can see a little bit of urbanization going on there. So on image C, it's very, very dark. So this is where the computer picked up some images, it picked up the difference in the values, and that value was negative in that area. So that shows that there is a negative change there, and that's the image that is created. And the last image is just a topographic area, topographic map of the area. Okay, my article that I did my project on was about finding an improved flood detection method in that city I can't pronounce in the country of Chad. They use ComSat-2, which has another name in South Korean. They use a ComSat-2 satellite. It is a South Korean satellite. It's not American. My article was in South Korean, but I cannot read that, so I got it translated. Let's see. There was a proposed method in this experiment to help improve precision and eliminate false detections. Existing methods were not as reliable. A data fusion contest was actually held to provide a new method to reduce errors such as image noise and other issues with spectral and spatial changes. This new approach differs from the original simple difference image subtraction that I explained from like the textbook images. The new method is a cross-fused image. So that means it's based on an analysis of the spectral distortion that occurs during the image fusion process. And image fusion is a process of combining relevant information from two or more images into a single image. This eliminates false detections, such as changes in newly populated urban areas. So if you just use the simple subtraction method, this would come up as, this would come up as a detection, because the computer doesn't really know the difference between any kind of change. So this new method proposed that it would not include changes that were not relevant to the subject that they were trying to achieve. Like they only wanted to focus on flood detection and not any other kind of change. It also provides, this method provided a better differentiation between flooded areas and permanent water bodies. So in the original simple subtraction method, many issues were being detected. They had a lot of false detections because it would just read these permanent water bodies as a change, even though it doesn't necessarily determine a flood. This is a completely new algorithm that it's just so complicated. It's something that would make my project presentation very, very long. So a lot of this information that I'm presenting is very, very summarized, but I assure you that algorithm is very complex. The goal of this experiment was to eventually lead to data that was best suited for a flood hazard map. The area of Chad is very flat and subject to flooding caused by heavy rain by tropical cyclones. This is predicted to become worse with climate change. A hazard map is to be made in efforts to be better prepared for this climate change. So the first image is the original water body in Chad before the flood. The second one is the image after the result of the flood. And then the third image is just the city in Chad that they did this research on. And these sets of images are all the different methods that I mentioned earlier, or that I will mention. So A, B, C, and D, and E are all the original methods that they had, that they did test, and then F, which is the very far right one, that is their proposed method with the cross-fusion image method. It detects the true changes in flood without false detections, such as having the original water body. So if you can see like the difference between E and F, E is fully covering in red the water body. And so whatever method that was, also D as well, D and E, they did not really do a very good job in detecting or not detecting the water body, if that makes sense. F, as you can see, it still can clearly see the water, the river that was passing through, and the only detection that came up was the actual flood. It didn't include any part of the original river that was flowing through. So the results, the proposed method and the new algorithm that they used was found to be most precise in flood detection than the original methods. MAD, CVA, SVM. MAD is multivariate alteration detection. CVA is change vector analysis. SVM is support vector machine. And they also did use other methods, but they didn't really go too much in depth. They really focused on just MAD, CVA, and SVM. This new method achieved lower rates of false detections, I guess, as you guys could see in that last image that I showed, due to its insensitivity to image noise. They also had the ability to differentiate flood events from the permanent water bodies. And they did propose to have further testing to be done in other urbanized areas to ensure the accuracy and precision of their method. And then these are my sources. My article is the first one. And then I also used the textbook. I mainly used chapters 2, 4, 5, 6, and 9. Those were most relevant to my presentation. And that is it. Thank you guys for listening.